Hello everyone and welcome to another lesson for the Chemistry O level. Today we'll be talking about elements, compounds, and the periodic table. So we'll start off with the definition of an atom. An atom is the smallest building unit of all elements. And it's the smallest particles of matter that we cannot break down further by chemical means. So an atom is the building unit for any element. It can't be broken into any smaller particles. An element contains only one kind of atom. So an element is a pure substance that contains only one kind of atom. For example, sodium. Sodium is an element made of only sodium atoms. Around 91 elements have been found in Earth and atmosphere, so these occur naturally. They are stable, they exist in nature, such as oxygen, hydrogen, sodium, helium. These are all elements that exist in nature. Scientists could make 27 other elements in the lab. These elements, or these artificial elements, aren't stable. They are mostly radioactive and they decay in a matter of seconds. And that's why they don't exist in nature, because they are not stable. So most matters that exist in nature are stable and or are found in stable forms. So these 27 elements decay and they are artificial. They are radioactive and unstable. All elements can be classified according to their various properties. A simple way to do this is to classify them as metals and non-metals. And here we have a comparison between these two. It's very important to understand the difference between metals and non-metals, because you have to be able to tell if this element with these properties is a metal or not. So, metals are usually solid except for mercury. Mercury is the only metal that's liquid at room temperature. Their melting and boiling points are usually high. It's the opposite for non-metals. They are solids or gases, except for bromine, which is a liquid at room temperature. Their melting and boiling points are often low. Metals are usually hard and dense, while non-metals are softer than metals, of course, except for diamond. Diamond is a non-metal. It's actually made of carbon atoms, right? But under high pressure and high temperature, it turns into diamond. So, carbon is like graphite, right? Under these circumstances of high pressure and temperature, the atoms of carbon rearrange themselves and form diamond, that very, very expensive substance. Their densities are often low because of their weight, of course. All metals are good conductors of electricity, and this is the most important difference between metals and non-metals. Non-metals are poor conductors of electricity. Of course, we have an exception for that, which is graphite, which is a form of carbon. But carbon itself is a poor conductor. Graphite is somewhat conductive to electricity. Non-metals tend to be insulators, of course. Metals are good conductors of heat. Non-metals are poor thermal conductors. Metals are malleable, which is very useful because we can turn them into different forms by hammering. And they can be pulled into wires, so they are ductile, such as copper. Copper is turned into wires for electricity conductance because it's a metal, as we mentioned. Metals conduct electricity. Because it's ductile, it can be turned into wires. Most non-metals are brittle when solid, so it's very hard to change their form, or when you try to change their form, it just doesn't give you the result you want. It turns into very small particles. But metals can be shaped. Metals usually make a ringing sound when struck, so they are sonorous. Non-metals are not sonorous. Okay, so that's a comparison between metals and non-metals. Oh, and non-metals, of course, vary in color. They have a dull surface, so they don't reflect light, while metals can be polished, so they reflect light when you cast light on them. And they are usually in gray color, except for gold and copper, of course. Now to naming elements. Of course, when writing a chemical equation, which we'll be talking about later, I don't want to keep saying the full name of an element. So I don't want to say sodium plus oxygen. It's too long and takes a lot of time. We need a simpler way to express chemical equations and to express elements. So scientists use symbols to represent elements instead of writing the full name of an element. These symbols are derived from the Latin names of these elements. For example, sodium is Na, for its Latin name is natrium. Pb is for lead, which is plumbum. And we need to realize something very important. The first letter of each element has to be capital. All the other letters, because elements can have one letter, two, or three. For example, oxygen is just O, sodium is Na, and so on. So the first letter has to be capital. The other letters have to be small. It's very important. These are basics of chemistry, of writing chemical equation, writing the name of the element correctly. All right, so we talked about elements. Now let's talk about molecules. Molecules occur when two elements are clustered together or joined together in small groups. That forms molecules. For example, in nature we see oxygen and hydrogen. These are gases that exist as a diatomic molecule. Diatomic molecule, from its name, di means two, atomic means atoms, so it's two atoms. So we have oxygen as O2, two oxygen atoms, hydrogen as H2, two hydrogen atoms. Okay. In the case of phosphorus and sulfur, for example, the atoms are joined in larger numbers, 4 and 8 respectively. So we have P4 and S8. Later we'll understand that these atoms do that. They exist as diatomic or in 4 atoms or 8 atoms to stabilize, as they are very active. So they form covalent bonds with each other to make them more stable. We'll talk about that later. Okay, so we realize that these molecules are made from the same atom. So these two H atoms and hydrogen are the same atom, all right? Now let's talk about compounds. Compounds are pure substances which are formed when two or more elements chemically combine together. So we have different elements. For example, water, H2O, that's its chemical formula. It's made of two hydrogen atoms joined with an oxygen atom. Okay, so you might be wondering, molecules and compounds are kind of similar. This table is just for your information. It's to distinguish the difference between molecules and compounds. By definition, a molecule is a group of two or more atoms held together by chemical bonds, right? Two or more atoms, the same element, while a compound is a substance, which is formed by two or more different types of elements which are united chemically in a fixed proportion. What does that mean? Let's look at water. We have H2O. It means that the ratio between oxygen and hydrogen is 2 to 1. So two atoms of hydrogen are joined to one atom of oxygen. That's a fixed proportion. All water compounds are made of that proportion, 2 to 1, hydrogen to oxygen. If we want to make a relationship between molecules and compounds, we can say that all molecules are not compounds, but all compounds are molecules. So yeah, in fact, water can be called a molecule and a compound, and we'll talk about that in a minute. Let's take an example for a molecule. We talked about oxygen and hydrogen as molecules, O2 and H2 as diatomic molecules. We also have ozone, which is O3, made of 3 oxygen atoms joining together. A compound, for example, is table salt, sodium chloride, NaCl. These are two completely different elements, sodium and chloride, joined together by a chemical bond and they form table salt. As for the structure, molecules are simply a group of atoms which are bonded by strong force, while compounds are actual matter in their complete shape. So NaCl is something that's existing, that has a shape, that has a structure, a crystalline structure. Visibility. A molecule cannot be seen with the naked eye, as they are the atomic level. A compound can be easily seen with the naked eye because you know that table salt, you can see that, and that's a compound. You can tell me that, all right, I see water. Yeah, you see it in its compound form. This example will hopefully clarify things for you. So is water a molecule or a compound? It just depends on what you mean by water. If you mean water in its atomic level, in its atomic structure, it's two hydrogen atoms combined with an oxygen or joined to an oxygen atom. So it's a molecule because, well, we don't have something called a water atom. We have a water molecule because these are two different atoms combined together, two hydrogen and oxygen. But water in itself, as the thing you drink in a whole, that's a compound, of course, because these are different atoms together. All right. Now let's talk about the periodic table. The periodic table just gives the name and symbols for the elements. Of course, it gives the atomic number and the nucleon number. More about that just in a few minutes. The column and row an element is in gives us a lot of clues about it. Yeah, it tells us a lot about its properties. These columns are called groups, while the rows are called periods. That's very important for you to remember and understand. You see this zigzag line. This zigzag line just separates metals and non-metals. So all of these are metals. After that zigzag line, these are non-metals. All right. So we have metals on the right side of the table, right here, except of course for hydrogen, because it's a gas, it's non-metal. And we see the metallic properties reducing when we go from this side towards that side. We're moving from metals to non-metals like that. Okay, now let's dive into the structure of an atom. We said that atoms are the building units of all elements. They can't be divided by normal chemical methods into smaller substances. All right, so what is the structure of an atom? Atoms consist of a nucleus and a cloud of electrons. That is the basic structure of an atom. That cloud of electrons moves around the nucleus. The nucleus itself is a cluster of two kinds of particles, protons and neutrons. While the cloud of electrons is, well, it's electrons, so it's made of electrons, negatively charged particles. All the particles in an atom are very, very light. And because of that, we can't measure their mass in grams. So we use another measuring unit called the atomic mass unit, short for AMU, or just U. Both are correct. Now, protons and electrons have an electric charge. All right, but what about neutrons? Neutrons, from their name, are neutral. So neutrons are neutral, they don't have a charge. So let's just check this table. We have a proton. It has a mass of 1 unit and a charge of +1. So protons are positively charged with a mass of 1 unit, so they have a mass, regardless to the fact that it's very, very small, but it's there, right? When we're talking about subatomic level, these things are very small. So when we compare something like a proton to an electron almost has no mass, right? So if something that has no mass is compared to something that has a mass of 1 unit, yeah, we take that unit in consideration, right? So a proton, 1 unit mass, positive charge. A neutron, 1 unit mass and no charge. It's neutral. An electron, almost no mass and a negative charge, right? And of course, because we have in the nucleus a positively charged particle, the proton, and around the nucleus we have a negatively charged particle, which is the electron. There is electrical attraction. There's electrical attraction forces between these two, between the positive and the negative, which keeps the electrons circulating and moving around the proton or around the nucleus. This figure here will show us more about the structure of an atom. So here we have the cluster of protons and neutrons. And of course, because protons and neutrons each have a mass of 1 unit, while the electrons have almost no mass, that means the whole mass of the atom is in its nucleus, because that's where the mass is concentrated, right, in the nucleus, because of the proton and the neutron. All right. The electrons circle very fast around the nucleus at different energy levels. These energy levels are called shells. We'll talk about that later as well. All right, so now we need to know about the distribution of the particles. I mean by numbers. All right. The number of protons in an atom is called the proton number, or the atomic number. The number of protons equals the number of electrons. All right, so we have the amount of positive charges equals the amount of negative charges, which means that I need you to pay attention. I mentioned the number of protons and the number of electrons. Why didn't I mention the number of neutrons? Because they don't have a charge, so they won't affect the whole charge of the atom, right? So we have the number of protons equal the number of electrons, which means that the whole atom is neutral. What about the nucleus? The nucleus has a proton, which is positively charged, and a neutron, which is neutral. All right, you said it. The nucleus is positively charged. All right, the cloud of electrons is negatively charged because electrons carry a negative charge. But the whole atom, the nucleus and the cloud together, the charges of the particles of the protons and electrons cancel each other, and the whole atom is neutral. Okay. Protons and neutrons form the nucleus, so they are called nucleons. All right. So the number of protons plus the number of neutrons equals the nucleon number. All right. From the symbol of an atom, we can tell its nucleon number and its proton number, because elements in the periodic table are written like this. In A, that's the symbol of an element, sodium, natrium, as mentioned before. We have 23,4 here, that's the nucleon number, which is the sum of the protons and neutrons. And we have the proton number here, which is 11, right? So we can calculate the number of neutrons. And here's how. We get the nucleon number, which is 23, minus the proton number, which is 11. That gives us the number of neutrons, 12. All right. Let me ask you a question. How many electrons are there? That's correct. We have 11 electrons as well. These 11 electrons are distributed in energy levels called shells. All right. I need you to understand something very, very important. In the periodic table, each atom has a specific proton number. So no two atoms can ever have the same proton number. I'm talking about the proton number, not the nucleon number, not the number of neutrons. I'm talking about the proton number. Each element has its own proton number. So only sodium has 11 protons. All right. In fact, in a period, each atom has one electron more than the atom prior to it. Let's go check the periodic table to make sure of that. Where is the periodic table? There we go. Let's check this one. We have here lithium and beryllium. Lithium has 3 protons, beryllium has 4. Let's go this way. We have boron, it has 5, carbon 6, nitrogen 7, oxygen 8, fluorine 9, and neon has 10 protons. So that's 3, 4, 5, 6, 7, 8, 9, and 10. Hydrogen has 1 proton. Helium has 2. Right? That's a period. As I mentioned, this row is called a period. Okay. This will be very helpful to us because now we'll talk about isotopes. Isotopes are atoms of the same element having the same number of protons but with different numbers of neutrons. Of course, they have the same number of protons because if you change the number of protons, you're talking about a completely different element. So an isotope or isotopes are atoms of the same element, so they have the same number of protons but with different numbers of neutrons. Let's see an example. We have carbon. Carbon has 6 protons and a nucleon number of 12, which means that we have 6 protons, 6 electrons, and 6 neutrons. This is an isotope of carbon. It's carbon C13-6. So it has 6 protons, 6 electrons, and 7 neutrons. Carbon 14 has 6 protons, 6 electrons, and 8 neutrons. Okay? Some isotopes are radioactive, and we call them radioisotopes. That means that their nucleus is unstable. When something is radioactive, it's radiating something, radiating particle and giving heat. And that is how atoms tend to stabilize themselves, because you'll soon learn that when an atom has high energy, it's mostly unstable. It needs to have lower energy so that it can be more stable. It loses that energy in the form of light, form of heat, giving up alpha particles, gamma particles, so many types of particles. And when they give out these particles, they are radioactive. And we call them radioisotopes. So giving out radiation in the form of rays and particles plus a large amount of energy. Notes that extra neutron in the nucleus of isotopes changes some of the properties of the atom, like its density, of course, because we said that a neutron has a mass of 1 unit, remember? So when we have an extra mass with that proton, the density will increase because the mass increased. But that neutron affects nothing when it comes to chemical reactions. Why? Because neutrons don't participate in reactions. Chemical reactions are bound to the electrons, and the number of electrons is fixed in all the isotopes because the number of protons is also fixed. So we have 6 protons, 6 electrons, 6 protons, 6 electrons, 6 protons, 6 electrons. The only change is in the number of neutrons. Okay. Radiation is harmful, of course, and continuous exposure to radiation causes radiation sickness. Symptoms include hair loss, vomiting, gum bleeds, and death. But we can use radiation to our own good. Let's see how. We use radiation or radioisotopes to check for leaks in oil and gas pipes. We add radioisotopes to oil or gas, and if a Geiger counter, which is this one here, it just we use it we direct it on that pipe, and if it detects a leak, it just makes a sound, all right? And it has a reading as well. So it tells us the amount of radiation that's detecting. If it detects radiation outside the pipe, it means that there is a leak, and if it doesn't, then there is no leak, right? So radioisotopes used in this way are called tracers. So we need to be aware that tracers are used to check for leaks in oil and gas pipes. We also use radiation to treat cancer. Yes, radiation can cause cancer, especially ultraviolet radiations from the sun. They can damage tissues and cause them to proliferate on a very high level, but we also use radiations or radioisotopes to treat cancer. Gamma rays from some radioisotopes kill cancer cells more readily than healthy cells because, well, when someone has cancer and they're trying to treat him, they direct a gamma ray on all the cells, the good and the bad, the healthy and the unhealthy. All right, so we need a kind of radiation that kills the bad cells on a higher level than the good cells, so that we don't have to harm the patient so much, or we don't have to face very high side effects to radiation therapy. Okay, so yeah, the gamma cells kill the cancer cells more readily than the healthy cells. The beam of gamma rays is aimed carefully at the site of cancer in the body, and we use cobalt-60 for that purpose. Radiation is also used to sterilize tools, as it kills germs and bacteria. So it's used to sterilize syringes and the disposal of medical equipment. You can also use the gamma rays to kill bacteria and sterilize food, right? So they also kill the bacteria that cause food to decay. So in many countries, food like vegetables, fruits, spices, and meat are treated with a low dose of radiation. It has to be a low dose, right? Because, as I mentioned, radiation is mostly harmful. So we don't really need to use a lot of that. Okay, so we use cobalt-60 and cesium-137 for that purpose. Alright, this video is already running kinda long. Thank you so much for watching. If you like this video, please don't forget to hit the like button, share this video with your friends, subscribe to the channel. If you have any questions, leave them in the comments section below, and I'll see you in the next video.